gonna be talking about multi-objective learning, and especially what I want to present is one unifying perspective on a lot of different types of problems that are of importance to fairness, collaboration, and robustness. So why these problems are all coming to be more and more important? Let's look here, so you don't see my next animations. Okay, so what's happening right now is that we have more and more data, and it's not just like more data arbitrarily, but this data that we are working with represents more and more stakeholders. So this data might be coming from different populations, different agents. And if you want to really be able to provide guarantees that is good for the whole collective of them, they have to really take into account their individual needs, individual guarantees that they're hoping, and overall kind of a bigger picture than like individual picture that's just more than the average picture. So what is an example of this? You might be thinking that, I have data that might belong to different subpopulations or people who are separated by geographic locations, race, age, and gender. So this might be different hospitals with representing really different types of populations of patients. And what we want is to, of course, be able to provide guarantees that hold for these populations. But that also means that we need to be able to get some of the information from these individual sources and then implement algorithms that work for these different individuals. So what that means is that there are many different layers to this question. Like it might mean that what we're really after is some form of data sharing. And data sharing has become really important in recent studies, especially for medical field, because some of the things that we are trying to do requires just so much data that no one center or no one medical center has enough data. So what we want is to be able to definitely bring data from different places that are representative of different types of people together so that we can actually learn across these things. It also means that it's not just bringing data from different sources, but also making sure that the learning guarantees that we're providing also hold on these different sources. So again, with medical research, but this is more broadly true, the types of solutions that we want to apply shouldn't just be good for the average person in the population, but it should be good for people who are separated by different localities, different races, or just kind of people who are faced with different sorts of threat models. And lastly, there is a type of a trade-off between the performance that different people wish or different centers wish to have and amount of work that they're willing to do or it's easy for them to undertake. So things that we see is that in physical domains, it's typically costly to actually get data, but data is also the way that you ensure better performance for different populations. So the questions that we should also be thinking about are, how would we make sure that the trade-off between the performance that a population is getting versus the amount of burden that we're putting on that population kind of makes sense for the applications we're doing. So
kind of on a big picture, you have in mind settings where there's multiple parties who want to collaborate but might have slightly different objectives. Not like one party controls things and another party is unhappy about that.
Yeah, you can, it's very high level right now. I will give you examples of why different pieces of this come in different places. So this cost benefit trade-off, I will talk about it only really towards the end. So for now, you can sort of forget about it, but focus a little bit more on if we want to provide guarantees that hold per groups and they're willing to come together to like provide resources. But at the end of the day, the type of guarantee we want is that it's either equally good or meets some bare minimum threshold for every group. What would that look like? So all of this is really in the backdrop is that machine learning algorithms, especially those that have been used and developed forever, tend to be very good on their performance on average, but not really good when you move beyond the average case. The reason for this is that the basics of kind of how these methods were developed we're thinking that we really want on average performance because either data is like homogeneous, like I have data centers that are representing people, or it's just that the data across people doesn't really correlate with any specific features that I wish to like protect. And this is maybe okay for data centers, but definitely not okay for socioeconomical data, or just human and organizational data. Organizational data is highly heterogeneous, and we do care about performance metrics matching or making sense across different sections of the population. So that's kind of the problem with the existing methods. And in fact, the existing methods, when you try to use them to extend to situations that can provide guarantees for different populations, they start acting really weird. And part of that is that there's certainly, as we said, populations are heterogeneous, but that heterogeneity also means that some populations have inherently easier patterns to pick up, and some have harder patterns to pick up, especially when you don't just think about one population, but you think about one population compared to all the other sources of information that you might be having. So that's why this type of on-average guarantees and kind of naive extensions of it don't work really well. And I give you some examples of real data where if you just kind of want to scale things up, you see that it's not going to really work. You cannot use on-average performance and scale it up well.
But I understand what it's about. So say if you think of a classification problem and you do like a base classifier where you actually know the probability distributions, but the base classifier overall would be the same as the base classifier for every subgroup.
So one issue here is actually the difficulty of learning the base classifier here.
So it's a finite sample issue that you're concerned.
Partly is a finite sample issue or finite resource issue. If you could learn a base classifier and the population agreed on their base classifier, then there is no trade-off technically. You could provide on average guarantees or not on average guarantees. But the issue is that there's essentially impossibility to really learn well that base classifier, and that's why you have to give something up. And when you give up things on average versus you give up things per population, the solutions start looking very different.
So in a sense, it's like a very limited conflict of interest here, right? It's not like a monopolist versus a consumer or something like that.
Actually, I will give you different examples. I'm going to talk about 3 different settings. And for one of them, there's very mild conflict of interest, as in there's no actual conflict, except that there's different levels of difficulty. For the other ones, there could be a conflict, and that's kind of the notions of fairness that come into play. People have decided that one notion of fairness perhaps is better than the other, and we'll talk about those. So I'll highlight them once I start talking about the different settings that we are considering, because they're slightly different from each other. Actually, let me start with 3 examples, and these 3 examples to some degree will highlight some of the differences. The first example is about calibrated or valid predictions. And calibration, I know that it actually means different things to different people. So let me start by saying what typically calibration might mean to one person. A predictor P is a function that takes your features and then spits out some value. You can think about it as a score between 0 and 1. That kind of represents the probability that you might represent some kind of outcome. Like it might be that you have trying to predict the risk of heart failure, and when I apply the predictor to you, that tells me what's the probability that you will develop heart failure in the next year. Now, a predictor is called calibrated if it kind of really means what it says. What does that mean? It means that, let's say that it predicts 0.1 on some number of people. Then if I look at the people whose prediction was 0.1, then about 10% of them truly develop heart failure condition. That's what it means for something pre-calibrated.
I think this is kind of interesting to connect yesterday to Karina's talk, right? About
I wasn't there yesterday, so yeah. But do you want to?
There was this whole discussion about bias versus noise and what is what, right? And so this is kind of a nice case of where calibration is conditioning on the prediction, but then nothing else. And I guess in this case, you only care about the bias and not about the noise. Yeah. Which makes the notion of calibration a bit funny, I think, because you can only care about part of the prediction effective.
So in fact, I wonder, even though I wasn't there, I wonder if this is what you guys were discussing. So this calibration, I mean, has been around forever and it's been influential in many things. One version of it, I have to admit that this is a bit of a caricature of calibration, but kind of a caricature of classical calibration might be a rather weak guarantee, because if I don't really differentiate between x's, what I could as a predictor output is just the average risk for everybody, for every single person. So that is a noisy, I assume this is what you were calling noisy, because across X is kind of meaningless, like me and everybody else is in this room, we are getting the same risk. And that's because, again, this is something that we are talking about on average holding rather than per, each one of us holding. So to make this slightly stronger, recently, we've been thinking about what does it mean to have calibration that holds per groups of people. So whenever I talk about per group, what you want to think about is I have some usually class of populations, this cursive S, and this could be any overlapping subsets of us in the population. The more of these subpopulations I look at, the finer guarantees I'm really going for. In fact, if each subpopulation was each individual one of us, I'm really asking for a very strong type of guarantee. So if I want calibration to hold in this such way, especially if S represented every individual one of us, then calibration actually becomes Bayes classification or Bayes predictor. But we don't have to go so far. We can, in fact, think about any subpopulation. And what we're really asking for is that we have this calibration holding, not just per predicted value, but per population of people that we care about. Okay. So not only what that might mean at a high level is that if I look at the risks interpreted for one population, that meaning is very similar to risks interpreted for another population. Since I know calibration is not something that everybody think about in the same way, let me talk a little bit about why it's important and what it represents at a high level and what it doesn't. So the reason we want predictors to actually mean what they say is because we use predictors for deciding treatment plans. One way to think about this is that there is some actual probability that each one of us will develop a condition. We don't know this, but we have a predictor. And the way we use this, let's say that this is predictor for one population. And the way we use this predictor is to say that, well, if your risk is high enough, I will apply a treatment to you. And if you're not having a high risk, then I won't. Now, what's happened is that there is actual empirical evidence that not only these predictors that we're using in practice are uncalibrated, but they're miscalibrated across different groups of people. So for example, this Obermeyer study, Science, I believe, 2019, showed that when you look at US hospital data, the risk predictors that are being used uses very different, like they're miscalibrated and miscalibrated differently across different populations. So for example, let's say that I have two populations, the blue population and the red population, and neither is calibrated. What the issue here becomes is that when I look at the treatment I'm applying to people, different people in terms of their actual Bayes risk are getting treatment at different levels. So the red population is getting treatment if their actual Bayes probability was this value, versus the blue population has to have considerably more actual risk before they start getting the treatment that they need. And the Obermeyer study found that within the hospital medical data, actually the Black population has to be considerably more sick to qualify for the treatments because of the miscalibration that's there.
So I wonder whether this is the same study that I cited, where it was a medical algorithm that was disadvantaging Black people with complex medical conditions.
Right.
It was Nature, is it?
It was Science, I believe.
Okay, maybe
Obermeyer, I think Powers and definitely Mullinaton and one more person.
I'm seeing your citation. Yeah, I mean, either way, it sounds
Might
like
be, it might be Nature, but for some reason I think about it as being Science.
That's, I mean, yeah,
I can find it.
say, but I was wondering, I thought one of the big problems there was just that we chose the wrong proxy to So rather a way of collecting data or designing the algorithm rather than like this.
That's quite possible. That's quite possible. So I'm going to focus on a different perspective here, which is less about did we take the wrong data rather than did we come up with an outcome, a predictor that was inconsistent across different populations. Because one way to think about this is, let me just show one thing here, is that one way this problem would have been resolved, doesn't matter what proxy we found, is that these two risks would have been closer to each other and both of them would have been calibrated. Because if you do that, once you apply the treatment, at least you're equally treating the different people. It might.
The question was calibrated for what, right? So if the Y that you have is not the right Y.
Oh, I think the proxy wasn't the Y. The proxy was what features were used for the actual
that study
study,
was
right?
using medical expenditures instead of actual medical needs.
Right.
And then poor people had less expenditures, and so they were
Yeah.
classified as less need. It's kind of, which is the Y in your notion, potentially.
No, the Y here would actually be the actual, so this is the actual probability that you will develop a condition. So that was a bad proxy. But if you look at it in terms of, it's also possible it's not the same study. But
So can I think of this as kind of counteracting the choice of a bad proxy?
if you can guarantee this, perhaps the issue is that if you pick a bad proxy, you may never be able to guarantee this. And I will highlight one place that I believe that might be the issue, but I'll bring it. So depends if the proxy is your X or your Y. If you pick a bad Y, you certainly might not be able to guarantee this, right? But if your proxy is more about which features to pick, I think then there's a different way of dealing with it. So this is like a caricature again of why calibrating across different groups will help you at least provide consistent predictions. Let me just say that you might lack calibration for many different reasons. These are actually, even though they're not calibrated, they're still nice calibrated, nice predictors because they're sort of monotone and linear. But you could have had a predictor that was constant and could have been calibrated based on what I showed in the last slide because of the noise, but it wouldn't have been a good one. Now, what multi-calibration is what I was saying here, which is across different groups of people. And intuitively, we are hoping for this picture. We want the predictions to mean the same across different groups. And one additional advantage of it is that while calibration alone can have this property that I was saying that can have really high noise, as you include more and more intersectional groups in your multi-calibration, as you essentially start looking at finer and finer guarantees, this picture becomes less of a reality and you start actually providing a more meaningful classification as well. More meaningful risk predictor as well. That's something I'm not going to go into too much detail because it's somewhat outside of the scope of what I'm going for. But at the extreme, again, if you think about S as being every individual, or every possible subset of individuals, you are really getting the Bayes classifier, which would have been exactly this. And what really happens here says that, well, if I had a constant prediction for some people, maybe that subpopulation would have been significant enough to be caught somewhere in my guarantees, and I would have also calibrated for.
But the definition of actual depends on what's in the axis.
What's in the S?
Well, what you put on the axis.
This is a toy example of what the picture looks like.
But your P star X, that's the definition of that. It's a function of what you include in the X, right?
For sure. This is like depending on your, but this is the Bayes classifier based on X. Okay. So this is at a high level why having more per group guarantees for this very natural notion of calibration is something that we might hope for. Yeah.
So here you assume that the groups are only defined in terms of observables, right?
Yeah.
What I assume is it clear that like if I have more of that in terms of observables and my group isn't directly measured or they're not using that helps, or?
That's a really good question. So just to make sure that we are on the same page, by observable, you mean that if it belongs to S, it only is a function of X.
Right, and so
right?
basically This seems related to the question of whether you use that X in your procedure, but like maybe a medical provider would not explicitly use race in the procedure, but it has implications for it.
Yeah, I will talk very briefly about this way into the presentation. Let me say a few things here. The way multi-calibration is defined is certainly defined by S's, as in you can have multiple classification. You might belong to multiple subgroups, but if you and I share the same exact features, we belong to the exact same groups of people, okay? This is not a big deal in the sense that there are slightly softer ways of defining this without losing any of the guarantees I was telling you about. This is just more about the way it's been defined in the literature. I'm not gonna go into detail about this. If you're interested in what does it mean to define it in a softer way, so that you and I might have different features, sorry, the same feature, but we could technically belong to different subgroups of people. That could be captured with, in some cases, without loss of any of the big picture we don't want to say.
And I guess the natural thing from an economist point of view would be to assume that there are unobservables in the subclass as well.
Yeah, the main thing that is important here is that if you and I have the same observable features, then the probability that we belong to a set should be independent of our unobservable. If it does belong to unobservable, things start to fail. There's a different notion of calibration. It's, I call it agnostic calibration. I think there's another name for it as well. It's considerably harder to guarantee, and it's usually not what any of the empirical studies go for. So that's what
So last question of that, because I'm curious, would there be a framework where it's observed, so say I know race, but I want to come up with a classifier that doesn't explicitly use race, but is optimized for being calibrated. So in training I can use it, but in deployment I can't.
Unfortunately, you have to. So, okay, so what does it mean? This is the part that I will actually talk about very, very briefly. The way you will then present your P is that you will say that, oh, I will look at what groups X belong to when I assigned my risk. In fact, it could look like something like this. If it belongs to set S, I will increase its risk. If it belongs to set S2, I will decrease it a little bit, and like this, okay? And that is somewhat necessary. It's necessary because there is also this kind of a framework in machine learning that says that you cannot have fairness without awareness of the groups that people belong to. If you remove the demographic population, you're more likely to create unfair treatments. So that's kind of why, but at least what I'm going to come back to is whether you need to have a lot of demographic information about any one individual, or on average fewer demographic information about any one individual. And I'll talk very briefly about that, maybe 40 minutes from now, okay? Yeah.
Are the groups defined beforehand, or do we have any idea to?
For now, assume that they're defined beforehand. I will also give you a pointer in situations that the group are not necessarily defined all a priori. Sort of figure them out as you go. Okay. Okay, so this is just kind of the high level picture of at least why calibration and calibration across multiple groups of people is something valuable and something we want on top of calibration. This is also the case for accuracy. For accuracy, it's easier to understand that, you know, of course, you want different populations to have equally accurate classification. And how you might want to measure classification or accuracy of the prediction here could be through a loss function. And this loss function could be binary classification, could be regression loss, could be one of many different losses. And what you, in the classical setting, usually you ask for is for this loss to be on average small. Okay, so maybe you want to say that the loss I have or the mispredictions I have is only 5%. But the issue is that, again, if you make an error only on 5% of the population, what it means is that on perhaps, 10% of the population, you're making an error like almost with 50%. So you're not providing any reasonable prediction for them. This is not problematic if this was some random 10% of people. You have to make mistakes, we understand that. It's much more problematic if that 1/10 of the people correlated again with those features that we wanted to protect. So then what would the per group guarantee look like? The per group guarantee would say that let's talk about any populations that I do need to protect. You could talk about them in terms of sets S, or you could talk about them as subpopulations of people in terms of different conditional distributions, D1, D2 to Dk. And then what you're asking for is for this loss not to be small only, but for on average, but to be small, still on average, but per group, okay? So if I kind of think about multiple individuals within the same group as being more or less the same, in the sense that the group is representative of them, then this type of guarantee makes sure that we are not giving very high kind of prediction loss to some group and very low to other groups. The third one is very similar to the last picture I was talking about, in the sense that you still have the losses that you were after. And what we kind of understand is that if I want to provide on average guarantees, how much resources do I need on average from people as well? This is something that, for example, number of samples or just information theoretic ways of thinking about learning addresses. It says that if you want to have such and such amount of error, your data set better be of this and this size. And usually the data set is collected randomly. What you might want to ask for is that, well, if I wanted to hold for every group of people, this different distributions, would I still fairly distribute the amount of information I need or the details of information I need across the groups, or perhaps it's unfairly distributed?
Can I suggest like yet another variation of those themes? Because I feel like there's all kinds of settings where you encounter much starker versions of the conflict of interest between groups. So, for instance, think of like a job, like a job recommendation algorithm that's matching job seekers with potential jobs, right? And then there's the question who gets which recommendations. And so, or like any type,
quota.
think or much more abstractly, like any bandit where you have a resource constraint, how many people can get which treatment arm, right? Once you're there, you have like a much starker
Yeah, that's definitely true.
But even if you knew everything that there was to be known, you would still have to make the trade-off. But whereas here, I mean, again, it's like primarily a finite sample issue.
Exactly. So for this, again, this is more about if I had infinite amount of resources, there wouldn't have been a trade-off. I would have been like equally well in terms of understanding the needs of every group. But because I don't have infinite amount of resources or infinite amount of I need to get resources from the population, and how would I spread that out?
But resources, you mean data?
Yeah. Data and also granularity of the data too. Because maybe from one population you're going to be a lot more intrusive now. Okay, so these are just 3 high-level examples. We're going to go into each one of them, mostly the first 2. But kind of the picture that they're really painting, I'm hoping that you get from this kind of an introductory part, is that what we're trying to do is that we're trying to enable a process that is satisfying multiple different objectives for different groups of people. And what we are hoping that we can do this is from collectively fewer resources, or at least given the fixed amount of resources we might have access to, how can we do this for more and more amount of individuals on finite grains? And this is a very practical consideration that's coming up in a lot of different frameworks, a lot of different actual applications. Data sharing and collaboration in learning is one of them that I was talking about, where you're actually getting data sets from different centers and you're trying to come up with predictions that are meaningful or equally good for those centers. There's an issue of robustness when you are thinking about deploying something in practice, but you aren't sure exactly what population of people it's going to be facing. So you wanted to be able to actually do fairly well across multiple different populations. And then there is the fairness issue, which is, again, it's a form of like ensuring either welfare or some kind of a collective utility for people when you think about people as being these populations. It's sets S and B. Okay, so what I'm going to do for the rest of the talk is that I will talk about the 3 examples in a little bit more detail, and actually show you how you could have one unifying framework that kind of helps us address the first 2 for sure, and it raises interesting questions about the 3rd problem. And I'm going to start with something called either collaborative or multi-distribution learning, which is closer to the 2nd example I gave, is considering accuracy for multiple groups of people, and is hoping to find accuracy that's equally good, or perhaps there are some trade-offs there if it's not equally good. Okay, so what is the multi-objective learning perspective here? This is how we think about per group guarantees in today's talk. I have multiple distributions representing different populations of people. This is D1, D2, Dk. And then I can sample from these distributions. I can identify these populations of people and actually ask for more information. There are also multiple types of losses or objective functions I'm interested in. Each loss could be something pretty arbitrary. One example of it is that maybe one loss I'm interested in is binary prediction. But in fact, there are some more complicated losses perhaps that especially become important for predicted value and calibration, where I care about the gap between the predicted value and the true value, but also I care about it only for some subpopulations of people. So in fact, both the losses we think about and these distributions can talk about different populations of people. One, in terms of D1 to Dk, is more like I think that I can actually access information about that group of people. The other, which is for the losses, doesn't necessarily say that I can access the information about any specific population, but I can still assess it. Okay. And then I will use capital L to talk about the expectation of this loss for the distribution and for the loss that I'm interested in. What multi-objective learning framework says and wants is that it wants to learn one function f. And right now, let's say that the fact that f is a single function is important. We can relax that. That is simultaneously good for every population and every loss function. What might that look like is that if I fix the population and the loss function, this is what I'm asking for. Now, I'm saying that no matter who was the population or who was the, what was the loss, I still have an upper bound. If I can guarantee this, what you should really interpret this as is that I'm uncovering something that's universally good for everyone.
Since you have that picture on the top, would I normally know which population somebody's from? Is that a feature available in the X? Or is there something where I can't use that information when designing the X?
It's something good. So instead of you could think about it as X itself is coming with some G, where G is representing the group of the person. Or you could say that I don't necessarily have it that way. Instead, what I say is that, oh, I want data for a specific G, and I go and I create the data, and then I append G at the end of every X that I created. So that's 2 different ways of doing the same thing. That data comes with the G, or you collected it in a way that you assigned.
But so I'm more like asking, it seems like, assume for the moment the loss function was just 1 and there were different populations. Then if my population is, if my X includes information on which population I come from, there isn't a conflict of interest, or like there aren't different optimal Fs that I would choose, but the optimal F would just be conditioning on it. So I'm wondering whether I should think of that tension or whether it's just a question of learning.
Good. Let me show one more line because that's where the tension might come in. So what I said is that if you could provide this type of guarantee, and the issue is that sometimes you might not be able to provide this type of guarantee. And what Jan was asking, for example, what could happen is that I have 2 different populations of people and their prediction is just completely opposite of each other. Okay. Like their true outcome, like the way that their Y correlates with the X, just completely different. If that's the case, I just cannot directly minimize this. So then one thing that you might be asking for is closer to this. What is this? It's saying that there exists an H that wouldn't have necessarily looked at the X's itself. Wouldn't have looked at the G's, which population you're belonging to when it was creating the prediction. And for that, what would have been the worst loss? What you're trying to do is not to have a loss that's any worse than that.
This is kind of like the Rawlsian.
Exactly. I was just gonna say that this is the Rawlsian perspective of fairness.
So I guess following up on Jan's question a little bit, I mean, I guess it does feel important, sort of, do I observe which group units come from? Units basically I are drawn, because I guess if not, if I do, then it seems like if I sort of had infinite training data, what I could do is just separately sort of pick the best F for D1, pick the best F for D2, pick the.
So think about it in the sense that during training, you're observing it, but your classifier cannot use that information.
Okay.
Like that. So that's the way to think about it.
Perfect. Yeah, so it's not, it's sort of not in X, at least for the deployment.
For the deployment, it's not.
Yeah.
When it comes to, okay, great question. When it comes to calibration, some of this changes slightly, okay? But for now, this is the right thing to have in mind. So what does it mean? What this could potentially mean is that when I apply my F to X, it can, and two X's came from two different groups, it cannot differentiate between them, okay? But it could differentiate on average. If, for example, more X's came from one group rather than the other, it could still differentiate on average. So your classifier F cannot look at the group membership, but because the training process could, it still depends on the overall guarantees. Okay.
And do you see this as kind of a kind of constraint in practice, for example, because we wouldn't be happy with using different rules for testing in different hospitals, or could this discussion also inform whether that's a good idea or not?
It can do both, in fact. So here is one place that I can use. Oh. One sec. Okay, I don't. This is probably not very easy to see anyway. Okay, it's not easy to see. So what I was gonna say is that it does both. So one place that this is important by itself is when there is some restriction, sometimes legal restriction, sometimes deployment restriction, that you cannot differentiate between people. A deployment example of this is when it's primarily about robustness, because you didn't know what population you were going to see, and you still cannot identify the population from small number of samples. There is also some legal situations. But let me say that when this objective is just really bad, but there was some other structure. For example, the structure could have been that I understand that, you know, the two populations are quite different from each other, but their base classifier, there was some relationship between them. And that relationship was something succinct I could be thinking about. Then slightly different objectives come to mind. I don't know if you can see these, but these two objectives are the one that I say, per population, I want to have guarantee for the best that was possible for that population. And what you could do is you can actually get these guarantees using this framework. I will not go into it, but I'm happy to give some references as to where you can do this type of a pointer. So it's actually a framework that I've seen, and I think we should be thinking about for addressing both of these considerations.
But just in terms of where the conflict comes from, again, right? I mean, one version would be what Jan was saying, that you can't use certain variables at deployment time.
Yeah.
But in principle, seems completely consistent. It's just saying there's some aggregate economic resource constraint, right? There's only so many kidneys to distribute or whatever it is. And
quota district. Yeah, like if your age was like implementing some kind of a quota, that also kind of makes sense. But yeah.
Exactly what the sets encapsulation.
I think it's like it makes more sense when it's less about division of resources for this and more about where there's inherent differences in how populations are presented in their X. Okay, like this is like an example that if we took an X that just didn't have important information for one population and had important information for all other population, this might start looking like, oh, for that population, my X just wasn't meaningful enough to capture something good. And then that's a situation that at the very least you would want to go into one of the ones I was showing. Okay. Cool. So let's go. So even though I said that there is different, oh, I need to do something again. What do I need to do? So do I
Scroll. Yeah,
I
thank you. Scroll back.
and then I
We
do
just
this?
magic resume presentation. No.
And I go from current slide maybe. From current slide. Oh, jeez. Anybody knows what I messed up?
Yeah,
You do?
no.
No.
What happens if you click from beginning and you got that?
I thought it would be more, we closed the.
Yeah,
it was-
No?
that's nothing.
And we-
Oh, hit the other button.
Which button? Maybe you want
How about the presenter button on the bottom?
like this?
Yeah.
No.
Okay,
Oh,
okay,
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 okay.
so that's going, yeah, yeah.
Okay, let's just pay attention, guys. Okay, good, good. Yeah, I'll try to minimize doing that. Seems very, okay. I wanted, it's thinking of, okay, good. Okay, so I wanted to write the two examples of multi-calibration, the way I defined it, and the multi-accuracy version. Both of them in terms of what the framework I just introduced to you. For multi-calibration, the way you want to think about it is that there is only a single distribution and subgroups are accessed through that S. This is somewhat important for the reason, Jan, you were asking that, and I was saying that each X, like if the two of us share an X, our group belongings are the same in multi-calibration, okay? And that's why we use S's to think about subgroups rather than different conditional distributions. But then the set of loss functions you really want to think about looks like something like this. It takes a predictor P and an XY value, and the loss itself is defined by the predicted value V, okay? The subgroup S, and this is sigma plus or minus that's really trying to capture, did I over-predict or under-predict on a specific group? So the loss would be something like this, over or under prediction, the gap between the predicted and real value, and whether the prediction fell in that calibrated bucket, and whether X fell in a specific subgroup of people. So that's the type of loss that you want to think about. And in fact, if that's the way you think about this, you have truly multi-calibration in the sense that your classifier is multi-calibrated if it fits that multi-objective framework that I said before. Now, in multi-calibration, because of the way we define S and X belonging to S, in fact, this min-max value is just 0. Because you could think about this as the Bayes predictor had 0 always matches PX and Y. And therefore, sort of the best predictor is really showing no trade-offs between the people. And you're just trying to deal with, again, lack of enough information when it comes to multi-calibration. Okay. What about the multi-distribution / collaborative learning? So this is the more general setting where you have now multiple distributions, but a single loss function. And you're just asking for the worst case distribution's loss to be close to the min-max. This, if they shared a Bayes classifier, would have been 0. But in general, it doesn't have to be. It could be something larger. Any questions? Okay, good. So this is just saying why the framework I introduced actually does capture the two things we are going to be interested in. Okay. In fact, the reason I wanted you to really see that general framework rather than just one of these applications is because of how much of a unifying perspective I think is playing across multiple different fields and different sort of lines of research, mostly from fairness, robustness, and collaboration. So from collaborative learning, or this type of federated collaborative learning people think about, where kind of data and guarantees are separated to different populations, this was introduced as a way of thinking about DIs representing different agents and agents who are willing to share some of their data with each other, but they want to get good guarantees for themselves. For federated learning, similarly, it was used, except that it was more of a fairness goal, not collaboration. It was less about actually actively providing resources and more like passively providing fairness guarantees. There is also something called distribution robust optimization that's been really important in the field of optimization. The idea here is that these DIs don't represent different groups of people. They're more like different potential futures that I want to actually deploy my model. And therefore, I want it to be robust to these different possible futures. There's multiple other works. These three are three different ways of, they're all related to multi-group fairness, calibration, agnostic pack learning, and a bunch of other things. They fall exactly in the setting I was talking about. This Rothblum-Iona is an example of what I was trying to highlight here, where you actually use the min-max objective to provide a slightly like pair group guarantee with respect to their own optimal kind of thing. But the main thing I want to say is that there are a lot more that I couldn't fit on this slide. So I think it's important to really think about multi-objective, really, because it's mostly the conversation in these different trains of research has been completely different from each other. They are not even connected. So I think it's important to bring them together. So what is the challenge here, even though this is what we want to do? And this is what I promised to very briefly show at the very least, is that we cannot just reuse old algorithms, the ones that do have good on average guarantees, even if I didn't have inherent trade-offs in terms of inherent conflicts in terms of what's the best possible. And that's because they become really inefficient in what they really are trying to do. So what happens is that, let's say, for example, this is a typical data set, in fact, a good one, where the groups aren't that far different from each other. And each of these lines is one loss for one group of people. What you see is that the types of on average guarantee that if you want to say, let's say you have accuracy that's more than 70% on average, you need actually very little optimization or number of iterations of optimization over your data sets that are being collected. But if you try to go for the worst case agent also being served well, it's not the existing algorithms. They don't at this point tell all the other distributions to chill, cool it off. You don't need to do any optimization. They in fact require everybody to provide twice as much resources and twice as much iteration.
So your horizontal axis is number of observations. So what's the axis?
It's actually number of iterations. So it becomes both number of observations and the amount of computational resources you're putting per observation.
Gradient descent type distribution.
Yeah, it's a gradient descent.
But like with a new observation every time.
It's stochastic gradient descent. So it's new observations, but then it's like mini batch, and then you do more per iteration, per observation as well. The more iterations you have to do. So this is kind of saying that even in a good situation that you might not be, what happens is that every agent has to do a lot more work to be able to provide the guarantee with existing algorithms for the hardest distribution to meet. And in fact, the issue really here is that the easier distributions, we are not really addressing the fact that there were some tasks that were slightly easier and just trying to focus more on the tasks that became harder. This kind of switching and realizing at what point who should be providing more samples and how our algorithm should start treating the difficulty of different populations differently is something that existing algorithms can't do. And there is actual theoretical and empirical issues with that.
It's related to like targeted exploration.
It's related to that, but it's actually more than that. So it's both targeted exploration and who has to actually provide even the computational resources here. Because targeted exploration says that I need to get information from very specific groups of people, which is absolutely the case here. And that's what we're going to see. But even how do you switch from combining the new information with the old information without losing the performance guarantees you were giving for the people who you're now paying less attention to is a challenge. Okay. Yeah.
I do not even understand how you would use creating this one to the small object.
Oh, all I'm saying is that just run it more. So one version, if there was no inherent trade-off, they were just kind of related in their base classifier, but difficult in different ways. You could always just run the average case guarantee for much longer. And what happens is that epsilon that's on average holding shrinks more. And because it's shrinking more, it's shrinking also per group, but at a slightly lower rate. So that's what actually current deployed algorithms do. Federated average is a style of algorithm that literally does that. And it's not working well. And I'll show you some examples towards the end as to why it's not working well at all. Okay. Let me go. I want to go a little bit faster to get to some of the issues. Was that a good question? Or?
Is that having different loss functions and different distribution completely different to different things? Or could I think of the different distributions as basically a change of measure that I can?
I like to think about them more like you. There is one slight difference, which is that if you have different distributions, you can actively sample from distribution. Whereas if you have different losses only, you cannot actively sample from them.
Because your training data is kind of coming from those
From, exactly. It's like any condition or not. Okay, so what we really want to do generally and in this talk is to say that we know how to do single distribution everything. I told you calibration has been known since 80s. Pack learning also 80s, 90s. We know how to do these things for a single distribution. Can we use the insights, the algorithms, whatever we understand from the single distribution case to things that we care about in the multiple distribution case. Okay, and that's the end of why this is a unifying framework. And now I actually want to show you how I use this framework to address multi-distribution learning and what is the way to solve them. So one takeaway that I want to have is what I was saying that the average things don't work well if you just run them longer is because the standard algorithms just lack interactions between different subpopulations of people and lack adaptivity. For example, what they do is that other than very specific low-level details, the number of samples they take, the learning rates they use, the update frequencies they use, is completely ignorant of the fact that there are multiple different types of populations. And these are decided non-interactively and non-adaptively. This completely ignores the difficulty and relevance. And what happens is that we actually can provably show that anything like running gradient descent longer or just anything that is non-interactive, it doesn't care about relative performance of two populations with respect to each other in an adaptive way, is going to suffer a lot in sample complexity or a lot in error performance that it can provide. How much? Well, you can sort of think about it as I wanted to solve K tasks, and I'm not getting any leverage from the fact that these tasks are related to each other or can collaborate. These agents can collaborate. In some sense, without an interactive protocol, multi-distribution learning is almost as ineffective as just learning every distribution separately without caring at all about the fact that there is something connecting these problems together. So this is particularly problematic for collaboration, but also problematic for fairness because fairness usually happens in environments where we don't have infinite amounts of data. What does interactivity really mean? It means that, and this is what I want you to think, interactivity and adaptivity come together, that to really benefit from cross-learning across different distributions, these distributions somewhat need to interact with each other. What I mean by this is that the decisions we are going to make about one distribution must depend on the relative performance of that distribution with respect to other distributions so far. Yes.
So this sounds kind of similar flavors like empirical base, where you try to learn how much variability there's across different units and then the optimal shrinkage to say a grand average versus the group specific ones.
It's possible. I have to
Right.
think more about
Like,
that.
I mean, like it's in the Bayesian framework, right? But like you have a hyperprior that specifies the variability across groups, say, and then for any given group, when you make inferences, you combine like the overall data and the group specific data, trying to optimally weight them in some sense.
I think it's a little bit more than that because that's more of a two-stage kind of adaptivity. This is actually ends up being a multi-stage kind of adaptivity. In fact, what we know is that you need to make decisions that not only care about the relative, but they need to care about relative at many points of decision making. So I think this is slightly more interaction than perhaps the previous frameworks talk about.
Is it different intuition, basically, right? In principle, if I just think about what's achievable with a single rule F, right? I basically have some Pareto frontier,
Yeah.
right? And basically, if I knew the slope of the Pareto frontier at the sort of min-max solution across the populations, I could just sort of do single population training, but with those weights on the pop, like.
That's a
sort of
very good
corresponding to the
intuition.
tangent.
That's the right intuition to have, that if I had a very good understanding of the relative trade-offs,
Yeah.
then I could somehow put that into my optimization, but that's not something I know a priori.
Right, and so I have
Exactly.
to
That's
learn-
the right intuition.
I have to learn the tangent. Got it.
So what is like one way of thinking about this is that what you're going to do is adjust sample collection based on past performance. And if you do this, what you're going to see is that instead of seeing it, K times as much resources or as much samples, you can get away with log K times. In fact, you can get away with less than this. Mathematically speaking, let me be a little bit more formal. What happens here, you're multiplying K, but I put log H here, it doesn't really matter. This is complexity of a single task. You're really multiplying that. Whereas here, you add a single task with a tiny thing that has nothing to do with how complex the task itself was. Okay. So how do you actually achieve this? And what is an interactive protocol? I like to think about it as game solving. And I already gave a tutorial 2 days ago that covered a bunch of these things. But let's just kind of do a short version of this. It says that I wrote this as some kind of a min-max. And when I think about min-max, I can always sort of hallucinate the existence of two different agents. One of them is minimizing. This guy is minimizing the loss over some class of functions. And this other hypothetical agent is maximizing the loss over the class of distributions. And if this is the perspective I have, very similar to what I showed in the tutorial, essentially what you could do is to find a good approximate solution with one of three different dynamics. What are these three different dynamics? It's each of these players, as long as one of them is playing something called no regret, which I defined before, but I'll briefly define again. And the other player either plays no regret or what's called best response, then the average performance gets to my desirable benchmark. And the faster I converge to this benchmark, the smaller the number of samples and resources that I would have needed. Because in some sense, in terms of implementation considerations, what I have is that the loss that I'm trying to actually play here is not something I know what it is. I have to estimate it. And to estimate, I need samples. And I also want to converge to this fast because the faster I converge, the fewer number of observations I'm going to need.
Can I think of this as a hybrid between like the stochastic and adversarial learning frameworks, where you're adversarial about picking the I, but they're conditional that you're doing sampling?
You could think about it that way. Certainly related to smooth analysis a little bit that I talked about, in the sense that, or you could instead think about the maximizing agent having quite a simple task because it's only picking one of K things rather than having full control over the distribution of this. Okay.
Oh, because they're picking it for only one time, not adaptively.
Oh, they're still picking
like
it adaptively, but they only have K choices in their adaptivity. In the tutorial I talked about before, they had infinite amount of choices. Okay, so what does this look like? When I say best response, what it means is that the choice of that agent per step is near optimal or good enough. And when I say no regret, it means that the utility or loss that she has is getting is near optimal over the sequence of the actions played by the other. So no regret, and hopefully you remember something from the tutorial before, but what it means to be no regret for the player that's minimizing and playing F1 to Ft is that he playing F1 to Ft and he saw some potentially adversarial sequence of which distribution at any time and what loss function. And the average loss that it got over T time steps should not be much more than the average loss of any one function he could have chosen. For the max player is choosing the distribution and the losses in an online fashion and is seeing some functions F1 to Ft, these are the predictors. Again, the average loss for the maximizing player should not be smaller or much smaller than the worst case distribution and worst case loss would have forced on the sequence of functions that were chosen by the other player. So this is what it means to be no regret. And we do know that we can provide no regret guarantees as long as the set is finite and small, it's easy to provide. But more importantly, the regret of these two players when they add to each other is the number, it's about the how fast you converge to that min-max solution that I was talking about. So you want no regret algorithms, you want them to be high quality, and you want them not to take many steps. So what does this look like? I described three different dynamics. Let's go from the first dynamics first. So what this looks like is that one approach is to have the minimizer algorithm, min player, to be best response, and the max player to be no regret. So what that means is that the best response player at every time step for any kind of distribution that the maximizing guy put over the k different distributions D is going to have to best respond to it, as in it's going to have to minimize the loss. You can think about it as minimizing the empirical risk. That's what this player is going to do. What the max player is doing, he has to be no regret. So what that means is that he has to maintain these alpha 1, alpha k at each time t. That's a distribution over the different k's. It's going to choose at random one of those distributions. And then what you really want to think about is that this alpha 1k at each time step has the relative, it's like a proxy for how poorly things have been off so far. It's kind of like the tangents that you were talking about, like how each agent was not being served well. To do this, of course, both players have to sample. This player has to sample because if you're trying to do empirical risk minimization, you need to know some information about the distribution you're trying to minimize risk for. And it's going to be this distribution. And what this guy has to do is to have a proxy for how poorly each agent is being served. So he also needs to kind of estimate their loss. So again, he needs samples. And interactivity is coming from the fact that we keep moving between these two things when you're deciding like what this guy is doing depends on this guy and vice versa. Okay, let me skip as to this proving that this actually works, because what I could do is to actually go back, instead of giving you exactly the number of samples, go back and this is because I don't have enough time to say that, well, one of them is no regret and his regret is fast. That's this guy, the guy who was choosing the distributions. And that guy only had k options anyway. So he is choosing things very fast. He's converging very fast. The guy whose best response actually has zero regret or tiny amount of regret because per round he's being optimal. It's just that we are going to converge really fast because of that. And per round, you know, the minimizer guy has to make some number of samples that's not trivially small. And that's why we get a sample complexity that's that log k times a single task. It's as if I run log k times. Each time step, I'm running a single distribution. This is dynamic number 1. I wanted to also show that, in fact, there is a different dynamic, the one that both of them play no regret, where things happen to be better. The reason here is that sometimes we use best response because it's good per time step rather than being good on average. And when things are good per time step, we have very good control over a dynamical situation as to how it evolves. First step, we understand it very well. But we typically don't need to have such a fine-grained understanding of the control problem. In fact, all we need is an on average understanding of it over many time steps. And if you play a no regret versus no regret, you could also get that type of a guarantee. In fact, the convergence rate is going to be what I said, the regret of the first player, the regret of the second player. The first player here has a regret that's very small. It's like, again, he has h many options available to him. So he has a regret that's log of h. The second player has to actually use a bandit algorithm. And what that means is that he has k distributions. Whenever he samples, he only sees one of them. So he needs to sample, he needs to understand every one of them. So that's a bandit type of optimization. And that's why you get k here. And if you put them together, you end up with something like this, which is the optimal way of doing this. So the two different dynamics actually gave slightly different sample complexity bounds. This is the dynamic 3 is the right one. Okay, what I want you to take away from this is that we are using this no regret online learning, not actually really because we have a true adversary into what we are trying to do, but more as a powerful medium for creating interactions across many different possible agents or distributions, as a way of understanding the trade-offs that weren't clear at the beginning at every time step. Let me talk a little bit about multi-calibration, because multi-calibration has slightly different types of challenges. And I already presented this to you, but in case you already forgot what multi-calibration was, it was the one that said your predictions need to mean the same. So if it's you predict 10%, then 10% of those people are going to develop a condition. And multi-calibration was this kind of a multi-objective learning where each loss cared about whether you were over or under penalizing something, what was the predicted value, and what was the subgroup. So there are some challenges and considerations that come into multi-calibration. One is that, of course, we need to have a no regret and best response algorithm, and how do we get them for such complex losses is something that is not clear. In fact, what we are really trying to do is for the minimizing player, we are asking, can I compute best response, which really means that, can I calibrate? Can I just have a calibration for a specific population and specific value? This is easy to do. This is like calibration.
Just a group average.
It's a group average. And group average for a possible random group, because this could be possibly randomly decided. So tiny bit more complicated, but still very easy. The question you might have is that, do I need a lot of samples to establish that? The no regret has similar challenges in the sense that you want to have a no regret calibration, but now it has to be against an adversarial sequence of choosing what population of people and what predicted values. You can ask the same questions in how much samples, or you can also think about how large is the regret, because both of them matter. For the maximizing player, you might want to play no regret or best response, the same questions come in. And finally, for multi-calibration, something that typically is desirable is that you want to output a single predictor rather than a distribution over predictors. I will tell you in a little bit why sometimes people care about this, but importantly, in the past, we aggregated, we time average solution, and sometimes for multi-calibration, that's not an ideal thing to do. So this is the type of challenge I will briefly talk about. This I will ignore. This I will highlight. So there are different dynamics as I was talking to you about. And what I want you to understand is that they actually have different trade-offs to the degree that each one of them might be relevant for one type of application. So really, it's important to understand these dynamics and the needs that you have before you choose how you want to go about multi-calibration. So let me go. These are 4 different considerations and the 3 different dynamics that we have. The first consideration is the one that is obviously about information. You're going to need samples. The more samples you have access to, the more freedom you have in choosing your algorithm. In terms of this, the no regret, this means that the learner, the person who was learning it, the agent responsible for learning the predictor, versus this is the agent, the maximizing agent responsible for finding the set that is miscalibrated. This dynamic needs a little bit more amount of information than either of the two other dynamics, okay? But I think this is something that is easy to decide. Do you have enough samples? Do you have enough resources or not? And then that can tell you why. The reason this dynamic is faster is because no regret to no regret converges faster. But the three other considerations are a little bit more subtle. The first one is that single predictor versus distribution over predictors. And in some applications, single predictor is really important. One example of this is if you're trying to predict something that is a higher moment, like I'm not just trying to predict your heart rates, but whether or not it's within one standard deviation of the mean, or is it more than one standard deviation? That type of prediction, it starts to depend on things that aren't just about means, but on variances as well. And having randomness makes those predictions less meaningful, okay? For those examples, you really want a single predictor, and single predictor can be guaranteed only in one type of a dynamic, where the predictor is using no regret and the adversary is using best response. The second consideration that's also subtle is how do you really implement this predictor P once you find it? And this is related to also the question that Yanni were asking earlier. I will call this succinctness versus interpretability with an asterisk that interpretability means so many different things. So what do I mean by this and what is it typically meant is that when you look at P is interpreted using some kind of membership, okay? So anybody who is an X, I'm going to think about what sets S it belongs to, because X is huge. If I want to implement my predictor, I cannot really write it down for each X. It has to be something that I represent at a higher abstraction. Like if you are belonging to this group, if your age is above whatever, I add certain points. If your race is whatever, if you're female, I subtract some points, and then I look at the final risk that I get. So I will call it more interpretable or succinct if you need to actually recall fewer demographic memberships when you implement this P. And if that's something that you care about, then no regret versus no regret, even though it gives you a random predictor, it turns out that it's much more succinct and therefore perhaps more interpretable way of thinking about your predictor. Whereas the other two dynamics are going to require more complex predictors, even if that predictor happens to be a single predictor rather than distribution. The last one was a question that came up earlier, which was, do I know the set of people that I care about, or am I discovering them? So one of these dynamics only, where the learner is best responding and the environment is no regret, is the one that can actually address this issue. And the way it addresses it is by saying that, imagine a situation where this you don't know which predicted value is really important. Perhaps you're going to figure it out because it's going to be close to a threshold of decision making, or which sets are really important. So somebody is giving you these sets and these values as they go. And if you're trying to catch up to that, you're essentially trying to have a robust predictor to the evolution of these considerations. And this type of predictor can be robust. These two cannot be robust, unfortunately. So this is just to highlight that different dynamics give different trade-offs. I'm not going to go into the details of the dynamics, but I'll at a very high level tell you where they're coming from. And they're coming from two things: how you can best respond and how you can be no regret from the learner perspective. So this is the guy who is trying to come up with a predictor, okay? We need to develop all the three dynamics. We need to make sure that we can actually do best response and no regret. The best response, like what Max was saying, is more like an on average guarantee, but perhaps for a randomized predictor. very similar to why we can, give just the average solution. We can also find such predictors. In fact, we can find them without even looking at the distribution itself. So I do not need to see any x's or any y's. All I need to know is which predictor, like which groups and which v's I'm trying to be calibrated for. The reason for this is that kind of if you know what population matters and which v is the one that matters, you could just try not to ever predict that v. Of course, this could be a v that is random, so you cannot just avoid those predictions, but you can make sure that they're calibrated easily. No regrets similarly can be made to work with three important things. The fact that when you have a no regret, your predictor P that is coming at every time step could actually be a single choice of P, whereas best response needed to have a possibly randomized predictor. And again, it takes no samples. So the only important bits of information from this are three things. The things are, I can actually deploy these dynamics, I can have a no regret, and I can have a best response algorithm for the learner. And they come very cheap. They do not take any samples, in fact. But also that the no regret happens to have a deterministic choice of predictor per time step, whereas the best response is using a distribution algorithm. And the last thing is that convergence is fast because regret is there. If you do this, what happens is that, going back to the previous slide, because I don't want to go over a lot of the dynamics. The reason you can get this single predictor here is that when you have the no regret learner, per time step that guy was choosing only a single predictor. And because the average of these predictors was good, one of them is good. So you can actually identify a single predictor. The reason this guy is using very few samples is because no regret not only didn't require any samples, but it was very fast convergence. So that's the reason this is small, is really because I'm using two no regret algorithms that are very efficient. The reason this is interpretable is because of how quickly you also converge. You're very quickly converging, and the sort of demographic information you need to recall at every time step is actually very small. It's just a single demographic information per time step that's coming in. So that's, again, the interpretability of it. So this is kind of at a very high level why different dynamics give you different types of trade-offs. And I think the way you should really be thinking about this table is not that you should always go with a specific type of dynamic, but what type of need you have when you think about this. Okay, let me go over quickly now. Oh, oops. Just kind of like the takeaway, just to think about the different dynamics and sort of as a way of unifying this. The last part of this talk is very brief, and it's because we know very little about this. It's mostly that there are interesting questions. So let me just go over that very quickly. This is about the trade-offs between accuracy and the amount of information needed per group. In physical domains like testing pipes for lid, medical research, the cost of data set curation is actually really high. Sometimes it's privacy cost, but a lot of times it's actual physical cost for doing something like digging a hole in your backyard, testing the pipe to see if there is any lead in it. And so what we want is that the protocol not only provides high quality per group types of performance, but also kind of has a reasonable burden of samples being shared across them, different groups. And what you want is to make sure that you're never asking for something that is undesirable trade-off for an agent between their performance and the cost. What is two different ways of thinking about reasonable or unreasonable share of data? I would call something unreasonable if I ask one agent to provide an amount of data or data set size that is more than what they would have needed to solve their problem independently without coming into a collaborative environment. This is the typical thing you call individual rationality for mechanisms. So the collaboration should never be more costly than individual solutions. The second part that I would say is unreasonable is if the agent has to contribute something that you could kind of think that part of their data set exclusively was used to help other agents rather than, or part of their effort was exclusively used to help other agents rather than the first agent themselves. This is what I would call stability because it's closer to a notion of equilibrium. I think there's a question about this.
I guess for the latter, right, I mean, in some sense, it feels like sort of a problem of contract design, but like you could imagine writing a contract such that, you know, the agent only gets the benefit if they contribute this piece of data. So it sort of doesn't help train the algorithm for them, but you sort of incentivize them in another way.
Yeah.
So I guess it's not.
So if you could provide actually like group specific solutions, it definitely becomes a contract design problem. The reason I don't think about it as contract design in this specific case, like go back to federated learning data sharing, you're outputting one model that's just going to be deployed on everything. So because of that, what's happening is more like they could free write technically by not doing anything, providing enough samples, but then taking the benefit of the model that's going to be deployed regardless. So but I agree that in some situations, absolutely there's a contract design problem and there are some interesting questions there too. I just mostly want to highlight the fact that even if you call these things desirable, both of them not only do not hold in current algorithms, they are invalidated to a very large degree. So for example, the stability, again, these are like ideal data sets. The groups aren't that far from each other. What you could see is that something like 60% of the agents could unilaterally shrink their contribution to like 50% of their current data set size, or current number of iterations they're willing to actually be in a gradient descent algorithm. And if even 10% of them do that, the algorithm is not going to even converge. So this is the type of thing, that's why I was calling it closer to Nash. They think that they can reduce their effort a lot. And if they do so, of course, the whole system will break.
And there's kind of a recent econ discussion about data externalities, right? Which is kind of exactly that, right? Especially when you think about it as actually individual level decisions to contribute.
Absolutely.
I mean, like the marginal benefit of adding data to the data that goes to zero, right? And so like
absolutely.
Everybody has an incentive to free ride.
Absolutely. So this is definitely a common problem because exactly, you know, it feels like if you have many agents, it definitely feels like you don't really need to provide samples. You think you can free ride. So that's definitely an issue.
And the flip side, if learning generates downstream harms, right? There's no incentive to withhold your data.
Absolutely. Yeah. So that's what I mean. I want to just highlight challenges rather than giving you solutions here because we know some solutions are very small. In terms of are these dynamics that I introduced earlier going to help with any one of these in particular? We don't know much, but as in formally and theoretically, observationally, non-interactive solutions are just horrible. So these are the ones that didn't even account for the difficulty. So they're going to create really bad trade-offs, in fact, and both stability and rationality are harmed by them. Between interactive ones, there's some reason to believe that no regret versus no regret is probably going to be a little bit nicer than the other ones. This is partly because of the fact that no regret versus no regret takes fewer samples at any one time and just has more iterations. So it's a little bit more sensitive to the evolution of the needs of an alpha, the different distributions.
Just a very quick logistic point. I think there's a seminar starting in this room.
Okay. Well, the question I was gonna say is that we can end here because all I was gonna say is that how should we really go about solving these problems?